Industries in Sri Lanka are trying to reduce their carbon emission because of the pressure from their clients in European and American countries. The carbon dioxide emission from electricity consumption plays a major role in overall carbon dioxide emission of industries. To achieve the net zero emissions targets, it is important to monitor the emission from power consumption, but in Sri Lanka there is no platform to monitor carbon emission or provide emission-optimized energy solutions. Thus, our team has decided to provide a solution for this problem under the topic of 24/7 renewable energy traceability for Sri Lanka. The quarter-hourly carbon dioxide emission and emission factor for the electricity consumption are calculated according to the IPCC checklist method. It shows total carbon emission values of the Sustainable Energy Authority in 2019 and calculated values with actual quarter-hourly generation data has 32.42% deviation. The possible reasons for the difference between the emission values are: the latest available SCA emission factor is for 2019. However, compared to 2019, 2021 has lower thermal generation, 50% hydro. According to CB, the SCA electricity emission factor is calculated based on the overall energy flow of the country at a macro level. In our model, the emission factor is calculated based on generation from each power plant. Emission factors used for each plant are obtained from IPCC's Special Report on Renewable Energy Source and Climate Change Mitigation. They might vary from actual emission factors. In order to develop the carbon emission forecasting, initially we use the AREMA model and then the LSTM. In the AREMA model, 108 days hourly data is used for training and 12 days as test data. The model forecasted the emission values for next 6 days. From the comparison with calculated emission data, the mean absolute percentage error was calculated 29.34%. In LSTM, 4 months hourly data was split into 113 days as training and 13 days as test data set. Then the validation of the testing data set for 1 week. Here the mean absolute percentage error for validation dataset is 19.17%, as shown in the graph. When considering the factors such as ability to identify the seasonality, most suitable time series data type, availability of data and ability to capture linear/non-linear patterns, the LSTM model can give better results compared to the AREMA model in this given scenario. Also, this clearly shows with the achieved results for mean absolute percentage error, LSTM model is the better option for the carbon emission forecasting on hourly basis. In order to reduce the carbon dioxide emission from electricity consumption, multiple power supply configurations such as only grid connection, with the solar PV and with the battery storage. With solar PV and battery storage, the maximum capacity of the installable solar PV calculated based on the available rooftop area of the buildings. The battery capacity is calculated based on energy consumption during high emission periods. An apparel manufacturing facility located in Kawata, Ratnapura is selected for this study. The energy requirement of the facility during peak hours is 1,268.50 kWh. The peak installable solar PV capacity is 896.88. The calculated battery capacity is 2,137.50 kWh. When comparing the CO2 emission from different configurations, grid connection only with solar PV has the lowest emission and grid connection only with battery storage has highest emission. Afterwards, a financial feasibility study was conducted with financial indicators of net present value, internal rate of return and levelized cost of energy. For all configurations, it was with considering carbon price value and without considering carbon price value to apply for the current Sri Lankan context, as well as considering lifetime 20 and 40 years. The highest NPV value has been received for solar PV only for all the cases, and the lowest NPV value is for solar PV and battery charge during daytime for all the cases except the case for 20 years. With carbon pricing, the lowest NPV value is battery storage during day charge only option. The highest IRR value for all the cases is for solar PV infrastructure. The levelized cost of economy financial indicator also again proves that the lowest LCO can be obtained for solar PV infrastructure. To conclude, to reduce the CO2 emission of the electricity consumption, Solar PV system is the most economically feasible option to implement for considered scenarios. The web platform provides visibility to grid generation and emission to the public and consumer emission profile for the client with login credentials. The generation data received from CEP and consumption data received from the industrial consumer are stored in an archive and read in every 15 minutes by the Node.js framework-based backend server. The quarter-hourly carbon dioxide emission and emission factors are calculated through Python. Using the calculated emission factors, the consumer emission is calculated. Then the ARIMA and LSTM models take the calculated emission values as input and predict the emission values for next 6 days. The backend server sends generation data and all the calculated data to the Prometheus database. Thereafter, the Grafana dashboard gets the data from Prometheus and plots in respective graphs. Finally, the React framework-based front-end receives the graphs displayed on the relevant interfaces. The grid generation and carbon dioxide emission can be monitored in the public interface in a quarter-hourly interval. The homepage firstly shows the generation data. This shows the fuel-wise generation. The graph is updating with 15 minutes time intervals. Using the cursor we can read the data as well. Historical data can be viewed by selecting the time frame. Here we can see the total carbon emission. Next it shows the variation of grid emission factor. The final graph updates the LSTM forecasted emission values. The consumer interface can be accessed from the login menu. Using the user credentials, industrial consumers can log into the private interface. Hourly energy consumption and CO2 emission of the consumer can be monitored here. Based on the consumer requirement, the interface can be further customized. Our web platform or the carbon emission monitoring and forecasting graphs can be integrated with any websites from the Grafana interface. Thank you.